Hey there, this is part 2 of our related rates video series. In the first video, I asked you to do this problem on your own to try the steps 1, 2, and 3. So draw a picture with variables, identify your d-whats, and write an equation relating the variables in the numerators of your d-whats. So the problem is water is being poured into a conical tank at a rate of 10 feet cubed per minute. How fast is the water level rising when the water in the tank is 3 feet deep? And we're assuming that the radius of the cone is half its height. So first, let's draw a picture with variables. So what shape do you have? What are we going to draw? We have a conical tank. And so let's draw that. So here we have a cone. I drew it this way because it has to contain water. It does say water, yes. So then, but we have to, so there's our picture with variables. So we have to put variables in here. What is changing? So as water is being poured into the conical tank, then the water level is changing, right? So if it starts empty, then you're going to have water that is filling it. And so the radius is changing. So when there's a radius here that's different than when the radius is down here. So we're just going to find a random level and say it's going to be here. So we're going to call this R. And then what else? The water level is changing. So let's call the height H. So we have R and we have H. Let me clean up some of this other variables here, just when I was explaining how things are changing. So you have H is the water level. So the water level is rising as time passes, and you also have your radius is changing. And so we know water is being poured in to the tank at a rate of 10 inches cubed per minute. So that is a volume. But anyway, we have our picture with variables. The variables are the things that are changing. So that will be step 1. Step 2, identify your d-whats. So we already said, okay, so water is being poured in at a rate of 10 inches cubed per minute. So because of the units, I can tell that this is a measure of volume. So that means that I'm going to have dv dt is equal to 10 feet cubed per minute. So now I also know based on the denominator that things are changing with respect to time. Okay, what are we looking for? How fast is the water level rising? So how fast is the water level rising? So I expect a rate of change that is positive because it's increasing. So we want, and that's where our variable comes in. So I want dH dt. dH dt is something, that's what we're looking for when the tank is 3 feet deep. So we want to know dH dt when H is equal to 3 feet. So that's what we're looking for. So those are our variables, and now we have our d-what. Notice that there's nothing given about the rate of change of R. The radius, nothing says the radius is changing at a particular rate, but yet I will have technically 3 variables. But we can notice here that it says assume that the radius of the cone is half its height. So we're going to use that in a little bit for step 3. What is step 3? Step 3 is write an equation relating the variables in the numerators of your d-what. So the only rates of change given to us are the rate of change of volume, and we're looking for the rate of change of the water level, the height of the cone. So that means that we want a formula that relates V, the volume, and the height in a cone. So that will be the formula for the volume of a cone, which is 1/3 pi r square h. And so this is where we're going to use the fact that is given to us about the radius, because otherwise notice that I have dv dt and I have dh dt. So when it says relate the variables in the numerators of your d-what, I need a formula with only v and h. Right now I have v, h, and r. So we need to somehow replace r. because I want just V's and H's in our equation. And so we're going to use this fact over here, that the radius of the cone is half its height. So that means that R is half of H. So we're going to put that in here then and rewrite our equation of the volume. So this will be 1/3 pi R square H, but R, we were told, is half the height. And so V is equal to 1/3 pi times, what's that, 1/4 H squared times H. So simplify it. So I have volume is equal to 1/12 pi and then H cubed. Now notice that I have a function with just V and H. Why do I want it with just V and H? Those are the numerators on my dw's. If something else in here told me, and the rate of change of the radius is something like 2 feet per minute, then I could put that in here and then I wouldn't need to replace the R. But because I don't know anything about the radius, I need to replace it. So now that I have the formula, with just the variables in the numerators, now we go to the next step. So the next step is take the derivative implicitly with respect to the variable in the denominator of your dw's. So have dv dt, dh dt. This should be the same variable in the denominator, so t. So we're going to take the derivative of both sides here with respect to t. So take the derivative with respect to t of both sides. And so what do we get? So I'm going to have the derivative with respect to t of v is equal to the derivative with respect to t of pi over 12 h cubed. Now remember here, right, they are functions of t. So v is a function of t and h is a function of t. So when I take the derivative of h cubed, I'm going to have to use chain rule. And so that's why we're taking the derivative of these implicitly. So dv dt then is, take the derivative of this, so I'm going to have pi over 12, that's a constant, so it just tags along with the h cubed, times 3 h squared, right? But h is a function of t, so times the derivative of h with respect to t. So that's where we are. And again, we're taking the derivative implicitly. So having h cubed here is like having h of t cubed. So how do you take the derivative of that? By chain rule, you have 3 h of t squared and then times h prime of t, right? That's the chain rule. So that's what happened here. I'm just not writing h as h of t, but that's how we're taking the derivative. We're using the chain rule there. So now that I have this, let's simplify as much as we can, just because it makes then our plugging in easier. So dv dt will be pi over 4 h squared times dh dt. So now we are to the last step, right? Because we already plugged in the value, or sorry, we already took the derivative implicitly, so now we're going to plug in the value. Evaluate at the specified value. So we want to know dh dt when h is 3 feet. And so we know dv dt, and we're looking for dh dt. So the rate of change of volume with respect to time is 10 feet cubed per minute. So I'm going to put that in here. So dv dt is 10 feet cubed per minute, and we're going to have equals pi over 4 h squared. So we want to know when h is 3, so 3 feet quantity squared times dh dt, and this is what we're looking for. So you're going to solve for dh dt. So let's see, so this becomes, so notice that again we're going to have feet cubed divided by feet squared, so that's just going to give us feet. So I'm going to drop the units for a second here. So This is 3 pi over 4, not 3, 9, because we're squaring it. Right, 3 square is usually 9, not 3 again, times dh dt. So how do you get dh dt by itself? Multiply both sides by the reciprocal of this, or divide by 9 pi over 4. Same thing as multiplying by the reciprocal. And so what are we going to have? So I'm going to have 40 divided by 9 pi inches per minute, not inches, feet. The previous problem had inches, so this will be feet, because we had feet cubed divided by feet squared. It's going to just give us feet equals dh dt. So that means that as you're filling up this tank at 10 feet cubed per minute, when the water level is at 3 feet tall, the rate of change of the water level is 40 over 9 pi feet per minute. Which, if you change that to a decimal, what is that? Approximately 1.41 feet per minute, rounding to 2 decimal places. So if you encountered this on homework, just make sure that you pay attention to how many decimal places are you supposed to round to. But this will be then the rate of change of the water level. So we can say the water level is changing at a rate of 1.41 feet per minute when the water level is 3 feet. Notice that if it's at 2 feet, that's going to be different, right? If you plug in 2 here, that will be 2 squared is 4, so you're just going to have pi dh dt, so it will be 10 over pi. So the rate of change is different, right? And that's the whole idea of this. As things are changing, the rate of change is different as you move, as time goes on. So that is another example of related rates. Let's try another one. We'll try this example next. So a boat is being pulled in by a winch on a 20-foot tall pier. The winch pulls at a rate of 2 feet per second. At the instant when the boat is 15 feet from the base of the pier, part A, how fast is the boat moving? And then part B, how fast is the angle between the water and the winch increasing? So again, try to set this one up, at least part A, draw a picture, put variables on it, right? What's changing? And then try to identify your d what. In the next video, so part 3, we'll start with this problem and work it out. But try it on your own again. Draw a picture with variables, right? Identify what's changing in your picture and put a variable on it. Don't put 15 feet on it because that's just at a snapshot. So you should have a variable. And then try to come up with your d what, and then an equation that relates the variables in the numerator. And then we'll see the solution in part 3 of the video.